Welcome back to Summer Work Help for Calculus 1. In this video, we're going to be taking a look at question number 12, and the directions for 12 are just simplify. All right, so for 12a, we have negative 5 root 2 times the quantity of 3 root 8 minus 7 root 24. All right. So for this problem, there's kind of two ways you can go about this in terms of first steps. So we can either, as your first step, you can either distribute and then simplify the square roots, or you could simplify the square roots, then distribute, and then you may potentially need to do additional simplification, right? So the advantage of the first method would be that it's only quote 2 steps as opposed to 3 steps. Because like I said, with the second option, if you simplify then distribute, you may have to simplify again. All right, you might have to simplify again. The advantage, though, of the second method is that if you simplify first, you'll be dealing with smaller numbers, so it might just make some of the calculations a little bit easier. So you could, if you want to simplify 3 root 8 and 7 root 24, because you can't simplify 5 root 2. That's as simple as you can make it. You could simplify this, and you could simplify this, then distribute. But I'm actually going to go with the first option here. I'm going to distribute, then just simplify. All right. If you wanted to simplify first, that's not a bad idea. But I'm just going to distribute. So just like you would in any other context, with the distributed property like this, we're just going to take this negative 5 root 2, all right, and we're going to distribute that via multiplication to the 3 root 8 and to the negative 7 root 24, all right? So let's go ahead and do that. Now, when I distribute like this, involving radicals or roots, I'm going to multiply my coefficients, and then I'm going to multiply the roots as long as they are the same root, right? And everything here is a square root, right? It's square root of 2, square root of 8, and square root of 24. You can't really combine different types of roots, right? So if this was 5 root 2 times 3 times the cube root of 8, that would be a different process, all right? But for this one, they're all square roots, so when I multiply, I can multiply my coefficients and I can multiply my roots. So first distribution. Negative 5 root 2 times 3 root 8. I multiply my coefficient. So I've got negative 5 times 3, which is negative 15. All right, so I'm multiplying the negative 5 times the negative 5 times the 3. And I can now multiply my roots. So I have 2 times 8, which is 16. So when I distribute the negative 5 root 2 to my first term, this is what I get for my first term, all right? Now my second term, I've got negative 5 root 2 times negative 7 root 24. So negative 5 times negative 7 is positive 35. And then root, 2 times 24 is 48. So I multiplied each of my coefficients, and I multiplied each of my roots. All right. So negative 15 stays there for a second. Square root of 16, well, this is nice because the square root of 16 is a square number. So the square root of a square number is an integer. That's basically what it means to be a square number. So the square root of 16 is 4. I'll use parentheses, why not? So the square root of 16 is 4 because 4 squared is 16 plus 35. Now I want to simplify the square root of 48. So to simplify the square root of 48, now 48 is not a square number. It's almost a square number because 49 is a square number, right? But 48 is not a square number. But it can be simplified, all right? And the reason it could be simplified is because 48 has as one of its factors a square number. Okay, so there is a square number that goes evenly into 48, therefore it can be simplified, all right? Now, it actually turns out that for 48, there's more than one square number that goes into 48. And again, when I say square number, technically 1 is a square number, but dividing by 1 doesn't change the number at all. So even though 1 is a square number, it also goes into everything. So that's not really useful, right? So we're going to, when I talk about square numbers, you can assume we're excluding 1. So if I want to simplify 48, I want to identify not just any square number that goes into 48, but I want to identify what's the largest square number that goes into 48. And I actually just thought of this. One way that you can do this is you can start at 48 and go down, right? So you can sort of check, what is the largest square number? But a number, if a number is going to go into 48, it has to be less than 48, or less than or equal to 48, right? So there's no point in trying, like, say 64, because 64 is a square number, but it's larger than 48, so it's not going to go into 48. Likewise, 49 is a square number, but it's not going to go into 48, all right? So the largest square number less than 48 is 36, all right? 36 does not go into 48, so that's not going to help. Then below 36, the next square number is 25. 25 does not go into 48. The next square number below 25 is 16. 16 does go into 48, all right? So that's the number that I want. I want 16, all right? 4 is also a square number, and it also goes into 48, but it's not the largest square number because 16 is larger than 4, all right? So we're going to go with 16. Now, to express 48 as 16 times something, right? 48 divided by 16 is 3. Therefore, 16 times 3 is 48, all right? So I've basically just rewritten 48 as 16 times 3, all right, equals. I might as well do this now. Negative 15 times 4 is negative 60, plus 35. You could break up the square root, but I'm just going to skip that step. The square root of 16 is 4. And then the 3 is still, like, trapped underneath the square root. So it has to kind of stay there. So I got negative 60. 35 times 4 is 70 times 2, which is 140, root 3. And then I can't really simplify that anymore. 60 is an integer; it's a rational number, whereas root 3 or 140 times root 3 is an irrational number. So those are kind of like unlike terms. So I can't combine them. And so my final answer for 12a is negative 60 plus 140 root 3. All right, B. B is kind of like A. It is like A, except now it's a binomial times a binomial. So A was a monomial times a binomial. This is a binomial times a binomial. Also, the numbers are a little bit larger. So this is probably the hardest question for This is the hardest part of question 12, I would say, is part B. All right. Also didn't leave you a lot of room here, so if you have kind of like big handwriting, you might want to get some scrap paper. So for B, like I said, this is a binomial times a binomial, and we've now seen this multiple times in this assignment. When you have a binomial times a binomial, you're going to want to use FOIL, which is basically just the distributive property 4 times, all right? So first, outer, inner, last. And again, when I multiply, you can, when you're multiplying involving radicals, you can multiply the coefficients, and then you can multiply the numbers underneath the radical, and then that will, that's how you do that multiplication. So we'll start with first. So first is going to be 10 root 35 times 4 root 21. I'm doing this, okay? So I'm multiplying those terms. So I'm going to multiply my coefficients. 10 times 4 is 40 root. 35 times 21. I would use your calculator. All right, use your calculator. 35 times 21 is 735. So definitely larger numbers than last couple questions. Then I'm going to do outer. All right, so this is the O in FOIL. So now I'm going to do this. Okay, I'm going to multiply that term times that term. Again, I've got my coefficients here. So I've got 10 times negative 9 is negative 90. Root 35 times 10. Well, when you multiply by 10, you just slap a 0 at the end. So this becomes 350. So you really shouldn't use a calculator for that one, because again, multiply by 10, just add a 0. All right. Next, inner. This is the I in FOIL. So we're doing these. 5 times 4 is 20. And then 6 times 21, you can do that in your head without too much difficulty, but if you want to use a calculator, go ahead. It's 126. All right. And then last, L, I've got 5 times negative 9 is negative 45, root, and then 6 times 10 is 60. Okay, so that's the FOIL part of this problem. Now I've got these square roots, some of which are kind of large, and I want to simplify them as much as I can. So 40. Square root of 735. So this is kind of it's a large number, and to be perfectly honest, this might actually be a good example of where instead of trying to like guarantee that you do this in like one step, you might just want to just sort of like experiment with like what square numbers go into 735, because I don't even necessarily know off the top of my head like what would even go into 735. So I haven't really done much of this yet, but I'm going to bring up the calculator. So we've got 735. So 735. And it's hard to tell right off the top of my head like what square numbers even go into 735. So one way to do this is just start experimenting and see like what square numbers give you, like what are the square numbers that when I divide them into 735 give me an integer. So the first sort of test value, we'll try 4, right? 4 doesn't go into 735, all right, because I get a decimal. Fine. Then, oh, hi Tony. Let's go ahead and turn off Teams. Forgot to do that. So Teams goes, where's Teams? Teams goes away. All right, no more interruptions. So the next square number after 735 or after 4 would be 9. 9 does not go into 735. Now I kind of, well, no, I know that 16 is not going to work, because if 4 doesn't work, then 16 is not going to work, but we'll just sort of prove that, right? And it doesn't. Another square number is 25, but that's not going to work. I can tell already. Nope. 36 definitely isn't going to work because 4 didn't work. The next square number is 49. And 49 works. 49 works, all right, because I get an integer. Now, I'm left with 15, and I actually know, because I get a 15, I know that no square numbers are going to go into 15, right? So 4 doesn't go into 15, 9 doesn't go into 15, and then once you hit 16, 16 is above 15, so it's not going to go in. So I actually know that not only is 49 a square number that goes into 735, it's actually the largest square number that goes into 735, because nothing's going to go into 15, all right? So I know that what I want to do is I want to rewrite 735 as 49 times 15, all right? Because 49 is my square number, 15 is what's left over, and sure enough, I do in fact get 735. So with larger numbers like this, you know, I consider myself to be fairly decent at math, right? I know a thing or two. But with a large number like 735, like I don't really know the square numbers that go into 735. So this is sort of the process that I would do just to figure out how am I even going to rewrite 735 as a product where one of them is a square number, right? So it took a little bit of time, but I think it was worth going over that just so you can kind of see the process of how do I write a number as a square number times something else. It's going to be 49 times 15. So let's get back to our work here. So we are rewriting 735 underneath the square root as 49, all right, 49 times 15. And you can kind of see in real time what the process was for how we did that with kind of a larger number, okay? Minus 90. Now, in the interest of time, I'm not going to do it again for 350. This might actually be a good opportunity for you to maybe pause the video and see, can you figure out, right, maybe using the process that we just did, right, what is the largest square number that goes evenly into 350? All right, so if you didn't know what to do before, pause the video and see if you can figure out what is the largest square number. Use a calculator if you want to, right? What is the largest square number that goes into 350? And then how can you rewrite 350 as the square number times something, all right? So pause the video, try that for yourself. All right, so it turns out that 350, the largest square number that goes into 350 is 25. Okay, so what we're going to do is we're going to rewrite 350 as 25 times 14. All right, so hopefully you had a chance to sort of try that for yourself to see if, see if you can do it. Plus 20. And we're going to do the same thing. Okay, so again, use this, pause the video, right? See, can you rewrite 126 as a product between a square number and some other number, right? And you want it to be the largest square number that goes evenly into 126. Pause the video, try that now. So the largest square number that goes into 126 is 9. And then you have a 14 left over, minus 45. You want to simplify root 60. I encourage you, try, pause it, see if you can do it. The largest square number that goes into 60 isn't that large, it's only 4, all right, but it is something. So 4 times 15, all right? So that step basically involved just rewriting all of the numbers underneath the square root as a square number times something else. Now, if none of the square numbers go into it other than 1, then you can't simplify it, right? Like you can't simplify like a prime number like 67, right? Like you can't simplify the square root of 67, right? So if you have a prime number, you can't simplify that because by definition, you can't write a prime number as some other product, right? So the rest of this problem isn't too bad. I'm not going to break up the square root. I'm just going to simplify. So the square root of 49 is 7, and then the root 15 has to stay there. Square root of 25 is 5. Square root of 14 has to stay there. Square root of 9 is 3. 14 has to stay there. And the square root of 4 is 2. And the 15 has to stay there. Okay. So we can clean up these coefficients. So 40 times 7 is 280. 90 times 5 is just 9 times 5 with a 0, so it's 45 with a 0, so that's 450, root 14. 20 times 3 is 60, and 45 times 2 is 90. All right, almost done, almost done. So we'll just do this over here. I can combine my root 15s and I can combine my root 14s. So I've got 280 root 15 minus 90 root 15. Well, 280 minus 90 is 190 root 15. And then I've got negative 450 root 14 plus 60 root 14. So that's going to be minus 450. 450 minus 60 is 390, but it's negative. So negative, or minus rather, 390 root 14. Going a little off the page, but that's why it's nice to have the tablet. So my final answer for B is 190 root 15 minus 390 root 14. Not an easy question, right? Not an easy. There's no algebra at all. This is all arithmetic. But not a super easy question, but doable. All right, doable. Multiple steps. All right. But yeah, simplifying square roots was kind of like the bulk of that problem, I would say. So that's my answer for B. All right. C. So for C, we've got, again, we've got a product involving two binomials. So we've got quantity 5 plus 2i times quantity 5 minus 2i. Little vocab here. These are complex conjugates. You don't necessarily need to know that, but complex conjugates are when you have a complex number, right? So a real part and an imaginary part, where the real part is identical and the imaginary part is identical, except one is positive and one is negative, okay? So we have 5 plus 2i and we have 5 minus 2i. Again, these are called complex conjugates. And the reason I point that out is because when you multiply complex conjugates, you actually end up getting a real number, okay? So again, I'll say that one more time. When you multiply complex conjugates, when you have a complex number where the real part is identical and the imaginary part is identical except they're different signs, so you have plus 2i and minus 2i, when you multiply them, when you multiply complex conjugates, the result is a real number. So the imaginary part is going to go away, okay? And we're going to see why that happens. All right. So, again, anytime you multiply two binomials, at this point, you really should realize that what you want to use is you want to use FOIL, right? Unless you have another way of multiplying binomials, right? But for me, I'm going to use FOIL. So first, outer, inner, last. So first, I have 5 times 5. That is 25. Outer, that's going to be 5 times negative 2i. So 5 times negative 2 is negative 10. And the I comes along for the ride. Inner, I've got 2i times 5. So 2 times 5 is 10. And again, the I comes along for the ride. And then I've got last, so that's 2i times negative 2i. So 2 times negative 2 is negative 4. And then I times I is I squared. Okay, so I want to clean this up. We've got negative 10i plus 10i, right? So those cancel. Okay, because they're identical but different signs, and so when you add them, those always cancel, right? So what I have left is I have 25 minus 4i squared. Now I said at the beginning of this problem, I said that the I part was going to go away because you're going to be left with a real number, right? So it's like, all right, well, did we make a mistake because there's an I here, right? We did not make a mistake because we're not done. And the reason why we're not done is because of what I means. Now, I said this in an earlier problem. I said this in 11D is when I first mentioned this. So I is defined as the square root of negative 1. Okay, that's just like the definition of I, which is the imaginary unit. Okay, now in this problem, our i's went away, but I do have I squared. Well, from this definition, if I were to take I squared, well, I would take my square root of negative 1 and I would square it, right? I'm just squaring the above equation. Well, when you have a square root squared, Well, those are like inverse operations, so they go away, right? So the squared and the square root cancel, and so I'm left with -1. So I'm left with this statement: I squared equals -1. Okay? I would encourage everyone watching this video right now, right? Unless you're like in like 6th grade and watching it for fun, in which case, hello. But assuming you're taking calculus next year, I would encourage everyone, to the extent possible, try to remember this. Okay? I mean, you kind of have to know this, right? You kind of have to know that I is the square root of -1. But I would encourage you, don't like derive this every single time you see an I squared. Just try to remember it, right? I is the square root of -1, so therefore I squared is -1. Okay, and then the I cubed is -I, and then I to the 4th is +1, and then I to the 5th is I again, and it cycles through, right? So like every 4, it cycles through square root of -1, -1, -I, 1, negative, or square root of -1, -1, -I, 1, and that just goes to infinity, right? But really, the first two are the only ones that you really need to know, right? So I is the square root of -1, and I squared is -1. So what we have here, getting back to the problem, is we've got 25 minus 4 I squared. Well, I squared is -1, which we just found that, right? So we've got 25 minus 4 times -1. Well, 4 times -1 is -4, and if you subtract that, you're really adding 4. So this just becomes 25 plus 4, which is 29. And sure enough, because we multiplied complex conjugates, we got a real number with no imaginary part. We just got the real number of 29. So from this problem, a little bit of FOIL, which you should know how to do. But then you want to sort of recognize, well, how do I handle I squared, right? And I squared is -1, right? So ultimately, what happens is when you see this, right? Given that I squared is -1, it's going to change your sign, and you're going to be left with +4, right? Because it was negative, right? But that I squared is going to change your sign to positive, so it's 25 plus 4, which is 29. Okay. D. So D, I've got quantity 3 plus 4I squared. So I'm squaring a complex number. Okay. Complex numbers have a real part and an imaginary part. And also those parts can equal 0, right? So like 7 is a complex number because the real part is 7 and the imaginary part is 0. Likewise, 5i is a complex number because the real part is 0 and the imaginary part is 5i. So all real numbers and imaginary numbers, you combine them, and you get the set of complex numbers. So I'm multiplying a complex number that has an imaginary part. So we've seen something like this several times now in this assignment, and if you want to skip this initial step, that's fine, okay? But actually, no, I'm going to do it. I keep showing this mistake because students keep making this mistake. This does not equal 3 squared plus 4i squared, okay? That is not true. You cannot distribute the squared to each term, okay? It just does not work like that. And students will continue to make that mistake, all right? And it's going to drive me up a wall. So don't be that student, okay? Make better mistakes. Don't make that mistake. So in order to avoid that mistake, I encourage you to write this out. And you don't technically need to do this, but it will help you avoid making that mistake and will make the next step a little bit easier, because now you can see, because we're squaring something, that means multiply it by itself. That means that we've got a binomial times a binomial, which means we want to use FOIL, okay? Which is the distributive property 4 times. So first, 3 times 3. I believe that's 9. Outer, 3 times 4i. 3 times 4 is 12. And then we have a single I. Inner, we've got 4i times 3. So 4 times 3 is 12. And then again, a single I. And then we've got 4i times 4i. That's last. So 4 times 4 is 16. And I times I is I squared. All right. So the 9's going to hang out for a second. We've got 12i plus another 12i. Well, I can certainly combine those. So that's 24i plus 16. Now I've got I squared. Now I just went over this in 12c, all right? So if you skipped over 12c, I would probably go back and watch it because I went into detail here. I'm not going to go to the same level of detail here. I'm just going to say it, all right? Because I is defined as the square root of negative 1, I squared, when I square that, the square root's going to go away and I'm left with just negative 1. And I would encourage you to know this, and I would encourage you to also know that. So I squared is negative 1, which means this becomes negative 1, all right? So that's going to cause that 16 to become negative 16, all right? We were adding it, but the I squared, which is negative 1, causes that last term to become negative. So what I've got is I've got negative 16. Now, it is a mathematical convention that when you have a complex number, which is what we're going to get here, you list the real part first and then the imaginary part second, all right? And I think that that's something that we're going to want to continue in this class, all right? Because that's a very strong mathematical convention. You write the real part, then you write the imaginary part. So I'm going to do the real part first. So that's going to be 9 minus 16. Again, that 16 is negative because of the I squared. So 9 minus 16 is negative 7. Then I'm going to say plus 24i. All right? And that is my answer. Okay? Now, technically, is that the same thing as 24i minus 7? Right? Yes, it is. But we don't like that. Right? So we don't like that. So don't do that. All right. When you give a complex number as your answer, okay. Now if you're doing the work and you're not done yet, and you have 24i minus 7, then who cares, right? If it's easier, then fine. But if it's your final answer, which this is, okay, you really do want to list the real part first and the imaginary part second, because that's a pretty strong mathematical convention. Okay. So our final answer is not 24i minus 7. Our final answer for D is negative 7 plus 24i. So if I zoom out, you can see all of our wonderful answers for question number 12.